Hello again. This is the Pencrest High School AP Physics 1 video series. This is video 4E, Planetary Mechanics and Highly Eccentric Orbits. Now we know already that gravitation and circular motion govern the motions of the planets and other objects in our solar system. Each of the planets orbits the Sun in an orbit that is nearly circular, not quite, but for the purposes of planetary mechanics, we can assume that it is a circular orbit. Now you're going to see a solar system data table. Using that data table, you should be able to determine any of the circular kinematics quantities for each of the planets, velocity and centripetal acceleration. You should be able to determine the net centripetal force on any planet and the gravitational force between any planet and the Sun. You should also be able to place a satellite in a particular orbit around any planet. So by particular orbit, we mean at a particular altitude. Now the trick to using the table is knowing what each column represents. The most important columns are the mean radius of orbit, which is how far the planet is from the Sun, and the period of revolution, which is how long it takes for the planet to go around the Sun. For the Earth, this would be 1 year. The only time you would need the radius of the object and the mass of the object would be when you're solving for surface gravity, or again placing a satellite in orbit around that planet. Now this is what the solar system data table looks like. Again, you see all the objects, major objects in the solar system. This Pluto, the table was made before Pluto got demoted a couple years ago. You can see this column is the mass of the object. Then we have the radius of the object, the period of its rotation, which we will probably not use at all. Then we have the two big ones, which are the mean radius of orbit and the period of revolution. These two are used primarily for any of the planetary mechanics, any of the centripetal kinematics or centripetal force. In fact, the mean radius of orbit is also used to determine the gravitational force between the planet and the Sun. Again, this mean radius of orbit is the average distance from the Sun. You can see it goes from the innermost planet, Mercury, out to Pluto, which is about 100 times farther away from the Sun. We also have these two columns, which once again would be used if you were placing a satellite in an orbit that was a particular altitude above, say, Venus. We would use the radius of the object plus the altitude to determine the orbital radius of the satellite. Now we're going to look at some highly elliptical orbits. There's an activity this week where we will simulate a comet, short period comet. We've seen that the planets have very low eccentricity, that is, the orbits are very nearly circular. There are other objects that orbit the Sun. They have highly elliptical, elongated, cigar-shaped orbits. They're called comets, and a typical comet orbit is shown below. This is not exaggerated for clarity. We already know what apogee and perigee refer to. The apogee is the farthest point from the Sun, which is here. The perigee is the closest point, which is here. On the diagram, note the labels C and A. C is called the focal distance or the focal length, the distance between the focal points. The Sun is at one focal point. The other one we know there's nothing there physically. A is called the major axis. It's the long measurement of the ellipse. The B, if we had one, it would be the minor axis, which would be up here. We have no use for that quantity. The eccentricity of the orbit, which is given the symbol lowercase e, it's a measure of how elliptical it is, or how squashed and elongated it is. Eccentricity is a pure number between 0 and 1 for our purposes. An eccentricity of 0 would imply a perfectly circular orbit. If you can imagine the two focal points being moved closer until they were effectively on top of each other, now we have a circle. An eccentricity of 1 would imply a parabolic approach, which is not technically a closed orbit, so we won't deal with eccentricities greater than 1. Mathematically, it's found this way: c over a, or the focal length divided by the major axis. You note, if you look at the diagram, you'll note that the apogee plus the perigee equal the major axis a. The apogee minus the perigee gives you the focal length c, so you can also represent the eccentricity this way. The orbital period can be found using Kepler's third law. We know that the r in r cubed over t squared implies there's a circular orbit. We can use the mean orbital radius, or the average distance from the sun, for elliptical orbits. And very easily we can take the major axis and divide by 2. If we know the apogee and perigee, add them up and divide them by 2. Each of those would give us the mean distance from the sun, or the r average. We would then use Kepler's third law, where the period equals the square root of r cubed over k. K is the Kepler constant for the given central object. We know the Kepler constant for the sun, 3.35 times 10 to the 18th in meters cubed per second squared. We would use that for any object that orbits the sun. Okay, so that is all. And that's all for circular motion. The next round will be work and energy. Until then, enjoy, and I'll see you soon.